Press R.
Okay, mi prendete. No, prego. Okay, so if we once we have this confirmation, we just wanted to remind what we have covered. So we did the oblique incidence upon an insulator, then we did a normal incidence first upon an insulator, then oblique incidence upon an insulator. But I believe we have not done yet the oblique incidence upon a perfect conductor. I believe we have not done that. And in that case, whenever we have an oblique incidence on a perfect conductor, in fact, in this case, we're just going to see, so to say, a simplified version of the results that we obtain from an insulator or a non-perfect conductor. So now, in this case, we have to say that whenever we have a conductor, we still have two options where we have the perpendicular polarization and the parallel polarization. So we still have these two different options. I believe this much on the board we can see. So we assume that this is medium 1, which is a non-conductor, and this is medium 2, which is what we're talking right now. And everything, it starts by writing down. So since here we're going to have no fields, we know that we have to write down the incident wave. Okay, and then we have also the incident, when we say incident wave, this is the electric field which represents the incident wave. This is the magnetic field representing the magnetic field. Then we're going to have the reflected wave. This is also the reflected one. When it comes to the transmitted, they will all simply be equal to 0. So ET would be 0, and HT, this is 0. I believe this much. We accept this. And then regarding the incident wave, here we have the Ki, the incident component. And let's do first the perpendicular polarization. So let's pick up this perpendicular polarization as initially. So perpendicular polarization, this means that on the plane, which is defined by the K incident and the K reflected, let's write this one KR. This is going to be the plane of the whiteboard, and we put in principle, we could say that this is the angle of incidence, and this would be the angle of reflected wave. But I believe so far we covered enough of incidence and reflection wave equations, especially when we did the incidence on a dielectric. We know that the incident angle will be equal to the reflected angle. But now, for the sake of the generalization, we can keep that on the board as theta I and theta R. And for the perpendicular polarization, we're going to have here, this is the EI, which is pointing out of the board. And let me see if I can find. So what is the direction of the magnetic field in this case? The magnetic field, it has to point like this. So this is going to be the HI. And the perpendicular wave here will also look like this, the ER. Sorry, the perpendicular polarization, which is represented by the electric field vector, which is going to point out of the board. And then what should be the direction of the magnetic field? It's going to be like this. So this is the HR. And this is in blue. This is the ER. So this is the complete configuration. And then we have to determine, in fact, XZ. Let's determine this is the X direction. The perpendicular direction is the Y, which is going to point out of the board. And here we have the positive Z direction. So it looks like the incident wave it is pointing, in fact, it's pointing towards at least the way that we have it here. So let's have a look at what is K incident. The K incident is defined, or this can be written. We can see that this is propagating along the AX positive plus AZ positive, okay? And this K, let's try to observe what is the projection of this K vector along the x-axis. So this is theta I, and this is going to be, someone can help me here, so what is the projection of K along the x-axis? This is sine theta I, and the projection of the K vector along the z-axis is going to be cosine theta I. Okay? And regarding the reflected K, the reflected K vector is pointing along the positive AX, so this is AX here, and along the negative AZ, so here we have minus AZ, but now we have to determine what are the, so here we have X and Z. If we draw this one here, this is theta R along the X, this is sine theta R. Again, we can write this reflected angle as R or I. We know that they're going to be equal based on the knowledge we have learned so far, theta I. So these are the K vectors. And in fact, actually, it's best if we write this one as a unit vector, because that's what it is. Because, and it's best if we do it like this, right? Because the amplitude of this vector is equal to 1. Because if we do the dot product of this vector with itself, we're going to get that this is sine squared plus cosine squared, we're just going to get equal to 1. So now, with this information, we can now write down the incident wave, which will be the following. This is equal to AY E incident 0 times E to the power minus J beta 1 times Kx. So here we have beta 1, and we have to include here x sine theta I. So now this propagator, this term that comes in the propagator, we try to extract it from here. So here we have x theta I plus z cosine theta I. So this is the incident electric field vector. We need then to determine also what is the H incident. So H incident, this is, we have to figure out where are the projections of these two, of this HI. And this one, it has a projection along the positive z-axis. So we have this vector along the positive z-axis. And also we have some component along the negative x-axis. And here we have the reflected H. It has a projection, they are both positive. So this is HX, this is HZ. And just for, to help us when we write down the vector, this is positive, this is positive. This is just a minus pointing that it is along the decreasing values of x, and this is positive. Now, we come here and we say that the incident wave here, this is equal to incident, or let's say EI0 divided by theta 1 times. Now we have to include the projection. So along the x-axis, here we have minus AX, okay, times, but this is the direction, but how much is this? This is angle theta I, this is theta, okay, let me write this theta I, this is alpha, okay. We say that alpha, I'm just using this to denote that the same way that I'm going to erase this one in a second. So I might consider this theta and this alpha just to keep in mind or to, in principle, just write that theta plus alpha is equal to pi over 2. Okay, so here this is theta, this is alpha. So the component along the x-axis, it is this amplitude, which is this one, this never changes. And then we have to multiply this hypotenuse with the sine, the sinusin, εκδίκονε alpha. What produce sinusin εκδίκονε alpha, pursued produce cosinusin εκδίκονε theta. So they are complementary angles which add up to pi over 2. So here we have with the second, so this is angle sine theta I. Am I right here when we say this? X cosine theta I, and then we have also this component which is going to be this one along the z-axis plus az times, it should be sine theta I. Sine theta I, this is just the amplitude. We have to include also the propagation, which is minus j beta 1 x sine theta I plus z cosine theta I. Okay, so this is the, and of course, this is again, I always just want to see something. Just give me a couple of seconds. Okay, so we are back. Now we have a eraser. So this was the components of the incident wave for the electric and the magnetic field intensity. Now, we could also, what we could do is that, in fact, we derive this expression quite intuitively because we know where it is standing, right? But we could also try to do the following. So the direction of the magnetic field, it can be written as follows, because we can have the following. We can say that H is equal to 1 over eta 1 K cross E. So we can also do the following. And we know that as a magnitude, this is how it should be. But we know also that if we have here E, H, and K, we know that any cross product between these three quantities, if we go clockwise, it is true. Now with this one, I mean the following. So the direction of the electric field cross product with the magnetic field intensity is going to give the K. Similarly, well, is this correct? This might even be wrong, this one, but let's check. We have also H cross K. This is equal to E. And K cross E, this is equal to H. Now, predominantly, kjo në ndihmon më shumë për të parë në fakt drejtimet e këtyre fushave, por magnitude, we know that the magnitude is going to be modified by whatever we have here, right? So we can do it like this, and then if this is the case, I believe this is true, at least for the sake of the direction, then this is going to be 1 over eta 1 times K. Now, regarding K, K is this vector here. So here we have AX times sine theta I plus AZ cosine theta I we do the cross product with E, which E itself is AY. Okay, so here we have the AY. And then to determine the correct results for this H, we could do the following. So here we have AX, AY, and AZ. And this would be like a cross product. Sorry, you cannot see all of it. Okay. So, and here we have K cross E. K itself is equal to what? What is K? K is equal to sine theta I. So this is sine theta I. The AY. This is cosine theta I. And then I believe we have no component here along the Y. And then for the E, the components of the electric field, it is only along the AY. So this is 0. And along the AY, we have we have these values, okay? And it is clear to all of us that the answer or the direction of the magnetic field is going to be as follows. So along the AX, we have here AX times, this is 0, minus this term, this is minus EI0 cosine theta I, minus AY. When we say minus AY, we get what? 0 minus 0, this is a simple 0, plus AZ, and here in AZ, we get simply EI0 times, okay, we really need, okay, times what is left, sine theta I. So we can factor out the common terms, which is EI0, and we can easily observe that this expression that we obtained here, it is exactly what, so what we got before, it is the same as what we are getting now, okay? So we can use either approach, but this is pretty good. Okay, so this is both intuitive and it is easy to handle. Now this was for the incident wave. We have to do the same for the reflected wave. When it comes to the reflected wave, we did an important part of the steps. So we have corrected, or we tried our best to identify the projection of the KR onto the orthogonal coordinate systems, which is X and Z. And in this case, we know the KR, and we try to identify now here what is the E reflected. The E reflected is going to be again the same, like AY times ER0 times e to the power minus j beta 1. And if we observe here, we just need to insert this k in these terms. So this is going to be x sine theta I, or actually we can even say theta r here, kan die reflectine, minus az, sorry, minus z, minus z cosine theta I. So this would be the reflected wave phasor, the phasor expression, which is not including the time dependency at all, but only the space dependence, or only the spatial dependence. Varsia spaziale, epsilon. And then we can also observe that the propagating vector between the incident wave and the reflected wave, it is changing only in the fact that the propagation along the x-axis is the same, so it's still pointing up. But it looks like it's going to change the direction in the z direction, which is true. So initially it was going along the positive z, and it is reflected backwards. This is where it reflects itself. Then the reflected wave, this is going to be equal to, we have projection along the positive x and the projection along the positive z. So we immediately write down, this is ER0 divided by eta 1 times, now part of these we could save them to get some use of more of the board. So the projection here, this is going to be equal to plus AX. This is, wait a second, yes. This is, no. What is, this is the HI, right? Yes, this is plus AX times. So we want to find out what is this component. This is theta r. Theta r, this is also theta. Okay. So theta, theta, alpha. If we use the notation of theta and alpha, they are complementary to each other, which complement them to 90 degree or higher. 2 theta, theta, alpha, theta. So this is AX times HR times cosine theta. Yeah, we did cosine theta here. Cosine theta I plus AZ sine theta I. So we could double check this one, but most probably this is correct. And then we have e to the power minus j beta 1. And now, of course, we have to write this this term, this propagation term into this expression. So now these are the two wave components of which this is all we can write here. Then we have to consider the boundary condition, which the boundary condition it simply states that the E1 is equal to E2, which means that but we have to consider the tangent components. Okay. So in medium 1, we should get whatever the wave is in medium 2, tangent component again. But we know that this is going to be 0 because in region 2 we have no real contribution. Okay, and we have to, in fact, maybe it's best if we, for the moment, let's write this theta r. Assume that we don't know that the incident angle is going to be equal to the reflected angle. Okay, and then what we need to write down is the following. So we should now write down this specific boundary condition, which will. So this is, we have to write only the components along the AX. Wait a second. No, this is, yeah. In fact, let me say something. If we write the boundary condition for the electric field, the whole amplitude, it is tangent to the interface. Okay, so this is the boundary between z equal to, or defined by the plane z equal to 0 and no, yeah. That's the plane between z is equal to 0. So this whole expression is perpendicular. So simply, let's say the following. From this boundary condition, we get that AY EI0 times e to the power minus j beta 1. Let's leave it like this for the moment. Plus the reflected wave, because we know that for region 1, in region 1, the electric field tangent component, it is composed of the incident part plus the electric field tangent component for the reflected part. Okay, this is all going to be equal to 0, right? And if we do that, we have here this term plus this other term here. This means that plus AY ER0 times e to the power minus j beta 1 times a complex of terms which belong for the reflected wave intensity. And in fact, what we can do is that, assuming that this boundary is at z equal to 0, if we substitute z equal to 0, it looks like these terms, they're going to, so this will be 0, and this is also 0. And what remains here is just x, we have beta 1 x sine theta I, x sine theta I, And here we have x sine theta r. X sine theta r, where theta r is the angle of reflection. Now, this is all equal to 0 because this is the detailed expression of this one. Now, we know one thing, that in order for this expression to be valid from minus infinity to plus infinity, or simply stated, in order for this expression to be true for all values of x, then we can say that because these exponential terms, a few discrepancy between two different values, this will contribute to a very large difference. This means that the only possible options would be the following, that this term, this whole term, should be equal to this whole term, okay? So these two exponential terms should be the same, and also the ER0 should be equal to minus EI0, which means that the reflection coefficient should actually be equal to minus 1. This is one condition we can get from here, and another, how can I say, not condition, but, probably this condition. So we get this, and also we get the following, that sine theta I should be equal to sine theta R, okay? Which implies, this second one, this implies that these two angles are the same, okay? Because, again, why would this be true? Because this has to be true when x is equal to 1, x is equal to 0, 0, x is equal to 2, 2. So whenever these values are changing, this will hold true only when this is also satisfied. Now, this was the first boundary condition, which probably this is all that we need, because we can simply derive also what is the reflection coefficient. Now, let's think for a moment. So we have here okay. Then we have to determine, in fact, this is the, let's see for a moment. This looks like these expressions that are written on the board, they are both true, only that if we have to rewrite this part again, we have to insert over there minus EI0I. So this term, now after applying the boundary condition, we know it. So then we have the following. The electric field in the first region is going to be equal to the incident electric field plus the reflected electric field. So we have to add actually the first expression and the third one. So if this is the case, let's see what we obtain here. We're going to get the following. So this would be equal to AY, okay? And then multiplied by EI0 times, wait a second, this is e to the power minus j beta 1. Let's write it like this. So e to the power j beta 1 x sine theta I times e to the power plus j beta 1 z cosine theta I, okay? So we just wrote this part, then we have to add also this part. Now, since we factor out this term, we get a minus sign here, okay? We get a minus sign because this expression would be equal to AY times minus EI0, and then the rest is not changing. Okay? So this is why we factor out this one, we get a negative sign, and we obtain that this is minus e to the power minus j beta 1 x sine theta I. Now we know that the angles are the same, so instead of this theta I, we do it sine theta I times e to the power, what we have here, this is e to the power minus j beta 1 z, we have to include here the z, beta 1 z cosine theta I. Now, if we see this expression, we can jump directly to the final conclusion, but what we can observe is that we factored out this term, but we could also factor out this one and this one. So, and then we have only these parts in here. So this is equal to ay times ei0 times e to the power minus j beta 1 x sine theta I times. Now we can simply, what we see here is that we have e to the power, so e to the power I theta, this is equal to cosine theta plus I sine theta, e to the power minus I theta, this is cosine theta minus I sine theta. Now I always write this on the board because I always confuse these. So if we subtract these two terms, what happens is that we lose the cosines, okay? Then we are going to get, if we subtract those, we get 2i times sine theta, okay? So we get a complex number term. So we are going to get here, wait a second, we have, but do we get a negative sign or it's plus? So we subtract these two terms, then we have sine, okay, this is, let's write the j, actually this is 2j sine theta. What is theta? Theta now is e to the power I theta, this is sine minus beta 1 x sine theta I. Okay, so this is a complete expression for the electric field in region 1. Okay, we have seen these types of expressions, especially when we had the standing waves, which were formed when an incident wave was reflected backwards from a perfect conductor. Actually, in any case, the complete wave, which is in one region, whether we have vacuum and the conductor, or vacuum and some other dielectric, always the field or the net wave on the one side of the interface, it is always equal to incident plus reflected. Okay, so this is something that we have to do it only in the case of this other region where we have a single wave, because what could we have on this other side? We could have only the transmitted wave, so we don't see much the contribution into adding these terms together. So in principle, this is the complete electric field E1, which means the following. As the incident wave is propagating, okay, let's say that we turn on, let me turn this for a second. So let's assume that we have a wave which is propagating in this region. And the only wave that we have before this interface shows up, the complete wave is this, okay, the incident one. But the moment that the wave, sometime t, after the first excitation of the initial wave, when this is meeting this interface, now a new wave is born, the reflected one, and that means that if we are to measure the intensity of the wave in this region, then one is going to measure the addition of this electric field and this one. Okay, so it's one which is pointing in this direction and one which is pointing in the opposite direction. Now, why do we say this? In fact, the electric field is going to point in this direction here, and it is going to be overturned right away, because we know that the reflection is equal to -1. So again, at each point where the waves are incident, we're always going to see this. The wave, it comes pointing up, and then it will return, because this is how the reflected waves behave. And of course, since this is a reflected wave, we can say that this is also a phase change. Ndryshon faza. Pra kemi ndryshim faze në pikën ku krijohet reflektimi I një vale, për sa kohë që vale ndryshon drejtim. Pra nëse mund të jetë duke treguar pozitiv epsilonin, më vonë nëse tregon negativ epsilonin, këtu kemi ndryshim komplet të vales. Okay, so this is something that we are observing. Then when we add that, this is what we get. Then the next really useful part of the possible calculations that we can do is the following. So we have the incident magnetic field intensity and the reflected magnetic field intensity, and we might also be interested into what is H1. Okay, so we found E1, which was a complete, I don't know which part we should erase, so for a moment allow me to erase this part. So then we would be interested in finding what is H1. H1 it should be equal to the incident wave plus the reflected magnetic field intensity. So we have to add together this term and where is it? And no, actually it's this term, incident 1. It's all the way down here. We have this one and this other term in here. So I have to add equation 2 and 4. So once we add these two together, the final answer is going to look a little bit complex, because this will be equal to 2 EI0 over the intrinsic impedance times the component along the, so let's see it for a moment. We have to add this term with this term, okay? Now, initially, it might look like these two are going to cancel each other, okay? This is minus AX cosine theta I, this is plus AX cosine theta I, and it might look as if they're going to cancel each other, but that's not true, because here we're going to have a negative sign, which appears because the ER and this one are not equal to each other. They are equal in amplitude, but not in direction. And in fact, here we should get a negative 2. Okay, this is more correct. So we have minus 2 EI divided by eta 1 by the intrinsic impedance multiplied by, so this AX term, this is preserved. We multiply this one with cosine theta I. So this term is still, which comes from there. And this is cosine theta I times cosine. Let's see what this is. This is cosine beta 1z. Beta 1z cosine theta I. Okay, and then we have also the projection of H along the z-axis, which can be observed easily here and here. Because we said that the H, it has a projection both on these two orthogonal components, orthogonal directions, which define the whiteboard that we have here. So here we have plus AZ, and plus AZ. But now here we have a complex term, which is J sine theta I sine beta 1z cosine. Beta 1z cosine theta I. Yeah. Okay. So, and we have one last term, which is e to the power j beta 1x, which is So this term and the x component which will come from here, this will be the e to the power minus j beta 1x sine theta I. Now, it is a good piece of work, actually. It takes some time, but all of these that you might be interested is that you can derive these two expressions by just simply adding the respective first equation, which we deleted now, and the second, which are these two, or to get this h1, we just add these two expressions. Now, what we can make use of the terms which are on the board right now is that we can make use of the E1 and H1 in order to find the time average power density, which is which denotes the energy flow. Okay, so the time average power density is the following. We can find what is this time average power density. This will always be equal to 1/2 times the real part of E cross product. So this is a vector with the H, but we should not forget that this H, this will be the complex conjugate term. Okay, so which means that we have to carefully pick up. So we have 1/2 times the real part of what? So real part, we have these terms. We can carefully write it down, and we observe that the complete electric field intensity, in fact, it has a complex term. Okay, so this itself. So for a moment, we can ask the following question: what is the real part of E1? Can someone answer this? What is the real part of E1, which is written at the bottom part of the board? So E1 is this, and the real part of this one is equal to 0, because all of the terms, they are multiplied by the square root of -1, which is j. So we are in principle asking the following question: what is the real part of e to the power I theta? This is simply going to be equal to cosine theta, or what is the imaginary part of e to the power I theta? This will simply be equal to sine theta. And it looks like the real part. Now, this is regarding this section. We're going to erase this one because this is only for demonstrative reasons. But let's write this again. The real part of E1 here is 0. Okay? And the imaginary part of E1 is anything but this j. So we just erase this j, and that's what we get. But this is what we observe for the moment. And then we have to do the cross product with h. Now, h is here. For a moment, it looks like, since we're going to multiply, and this is E1 and H1, we have to take the complex conjugate terms of H1. What is the complex conjugate of e to the power I theta? This is in fact, this is equal to e to the power I theta complex conjugate. Okay, we just missed a little bit. Let's see it like this. Or simply, we can say the following: the complex conjugate of 3 plus 2i, this is equal to 3 minus 2i. So the complex term, they change sign, etc. So this means that the complex conjugate of h1, this is going to be a minus sign, just to track down what changes are going to happen in this expression. So we have here minus j sign. Then we know that these are going to be multiplied with this j here. So this j in here will be multiplied with this minus j here. But there is another minus which stands up somewhere here. And j times j, we get, well, let's count the minus signs. We have one minus sign here, one minus sign here, and one minus sign which will come up from the multiplication of j and j, okay? And if we multiply all of these terms, let's just see for a second. We have to have the following. Let's see. And also, we should not forget the amplitude of this term here with this term. So we are always going to the term of EI0 square. This will always be there, and the rest it will include, because we have to consider the real part. It has to include also the direct multiplication of the. This is this term here we multiply this one, and also sine theta I, sine theta, and the sine squares also will survive in the final term, and let's see that we're going to get. So again, since we have to consider only the real part, most probably we're going to get this term and this term surviving. The multiplication, which is going to give sine times cosine, this is not going to survive because this is j times a term which is not j. Maybe it's best if we do it like this. Let's try to summarize it as much as we can. So first of all, we get here 1 over 2 is always there. But then another essential part is that we have to identify what is the direction of EI with H, E1 with H1, which is going to show the effective direction over which the current is going to flow. And if we follow the calculations carefully, we're going to notice that the effective cross product between the terms is going to be AX, because here we have electric field AY, cross product with AZ, we're going to get here AX. So we go the direction, we get that 1 over 2. We have to multiply the amplitudes, so here we get 2. EI0 squared over EI1, right? The amplitude is this term and this term here. And then times sine theta I. And this is sine squared theta 1z cosine theta I. Okay, so this is the time average power density. Yeah. Now, I want someone from you to answer the following question. Why do you think we have a flow of the energy only along the AX direction? You can raise your hand and I can pick up someone from the class. Amina? Amina Tatari or Besmiri? Or Ismiana? Okay. Ismail, can you answer this question? So the question is, why do we observe an effective energy flow along the AX direction? Okay, you prefer to write in the comment section rather than use the microphone. Let me have a look. Maybe others will cancel out. Yes, Amina, but when you say others, you mean what was the other possible direction of the energy flow? You can answer by writing down in the comment section, Amina. That's a first try, it's a good option. You can say that the others will cancel out. Okay. But which direction? Okay, so Z. So you're right, you're saying that Z will component will cancel out, okay. And only the X is surviving. So it looks like effectively we have some energy flow which is flowing. I mean, if I show the energy flow at the interface, we could say that there is some energy flowing up, okay. So this is what we are observing on the surface of a metal. So we have an interface here, we have an incident wave, reflected wave, and in the end, it looks like in the boundary or at the interface, the energy is effectively flowing up. And this is also, we can provide two types of answers. One type of answer is the intuitive one, which is just based on the approach of what a wave could do. And we could argue on that since this is a conductor, let's assume that the wave is composed of two vectors. One vector, which is the perpendicular vector like this, okay, and the other one is reflected backwards. We did before, when we covered the normal incidence of a wave that is incident on a perfect conductor, we had no flow of the energy, right? So the time average power density when the incident wave was normal to a conductor, we noticed that this was equal to 0, okay? Because all the incident wave was reflected backwards. Now, what we observe here is that the component of the wave, which is represented by the Ki along the Z. So let's consider where is the Ki along the Z. It is this term, okay? So whatever current is moving along the AZ will be reflected backwards like this, okay? If we assume that this wave was not oblique incidence, but it is normal incidence, this is what we're going to have, right? This means that K incident is AZ cosine theta, and KR is like this. That's good. And this would produce a standing wave or zero flow of energy in any direction. Okay? But we have also these terms, which, how much do they contribute? They contribute, I don't know if I can write this one, let me use a rhombus like this. Using a rhombus like this, we observe that we're going to have an effective flow of the wave along the AX. This is the answer, which is based only on the intuitive analysis of how the waves propagate. Another answer is the mathematical one. So you just give it to a student, they know nothing about the wave or how the wave propagates, but you tell them, you have this E1, which is this term here, which is a pure complex number. It's purely complex number because it's j times some constants. Multiplied by these terms, what we conclude from them? We conclude that if this is the real part of the magnetic field intensity, we multiply it with a purely imaginary part of the electric field. That means that we get the complex part when we multiply this with this. But if we multiply a purely imaginary part, where we have this j here, with another imaginary part, we know that when we multiply two imaginary parts, we get a real part, because j times j is -1. So if it is a real part, we know that the time average power density also considers only the real part, which immediately reminds us that the final product, it should be a multiplication of the terms which are currently in the imaginary section of the wave. What are in the imaginary section of the wave? We have here sine theta I, and here we have sine theta I, and this is why these survive here. Actually, sine theta I, is it squared or not squared? Apparently, it's just sine theta I. Why is it like that? I don't clearly see it myself, but the answer on the board, it should be correct. But for a moment, I'm just wondering Standardized. Complex part is here, they multiply. I don't see it exactly right now. I can't see it for the moment. Okay. There's something I'm missing for the moment. There's at least why we don't have a square here. If we do the calculations, probably all of us will easily notice that, but yeah. Let's leave it like this, as it is on the board. Okay, so and in fact, in this case, what is also sometimes worth looking at is the fact of what is going between the X and Y components of the electric field and the magnetic field. Okay, so this was the perpendicular polarization. We can do this complete same analysis for the parallel polarization. And for the parallel polarization, we would this graphics is going to change, where the electric field is going to be on the board. So, looking at this picture that we have currently here, probably it is best if we just draw them next to each other. So let's take this. So if we draw this one fast, we draw this fast because it's simple, not because it's difficult. So we have an incident wave here. We said that the electric field now is going to point to be parallel polarization. So the electric field, let's do it like this. This is the incident electric field. The wave is going to be incident here. It's going to be reflected backwards. This will be the KR, the reflection vector. Then the ER is going to be this. This is the E incident, and then what remains for us, it remains to draw the magnetic field intensity. This is K cross H. E cross H. We should get K, which means that K it should point out of the board, and when the wave is reflected backwards like this. What should be the direction? Let me see for a moment. So, if we assume that the magnetic field is pointing, okay, so it looks like the magnetic field intensity for the reflected wave is going to point into the board, okay? So, this is H incident, HI, this is HR, and then after we do this, let's preserve the same directions as we had over there. This is the x-axis. This is the positive z-axis, and it looks like there is no difference in the projections of K incident and K reflector. They will be the same as these terms. Again, this is a conductor, so nothing, so let's say sigma is much larger than 1. So we're not going to have a transmitted wave, and what else we can say? I mean, the next step is simply starting and writing down what are the important terms which should be. Actually, let me take this out for a moment. If you have any questions, please, you can either comment using your microphone or writing in the chat section. Let me have a look here. Yes. So the situation would be simply, again, incident electric field. This is a vector. This is going to have, looks like the incident electric field is going to point to have a projection along the positive AX. So let's write here actually this EI0 times positive AX, and we have minus AZ because this is pointing along the negative AZ, positive AX, and here we have that the reflected wave, it is along the positive AX and the positive AZ. So if we write them like that, this is the reflected wave, this is going to be ER0 times AX times some terms plus AZ times some other terms. Let's see what these terms are. For this, so this is theta I. If this is theta I, this is alpha, this is theta, and the projection along the AX is cosine theta. So here we have cosine theta minus AZ. We say minus AZ because this is strictly pointing along the negative Z values, assuming that the positive Z is pointing to your right. Then here we have minus AZ, but how much is this? Is it sine or cosine? Most probably should be sine, so here minus AZ sine theta I. Then we have e to the power minus j beta 1 times what? Times the propagation factors here, they will be exactly the same as they were for the case when the polarization was perpendicular, okay? So we can simply say that this is minus j beta 1, we have here k beta 1, then we have x sine theta I, x sine theta I, plus z cosine theta I, plus z cosine theta I, and the reflected wave, this will be, I think this is also, this is theta R, theta, alpha, theta. This is how we can read the angle, so this is theta, 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 yes. So along the AX, this is cosine theta R, this is incident theta, incident. This is sine theta R e to the power minus j beta 1. And now this beta 1, for the reflected wave, we read the configuration of this ki, which is going to be equal to, this is x sine theta I, I'm sorry, x sine theta R, actually, because this is the reflected wave, minus z cosine theta R. Okay, so this is the reflected wave. We immediately go and write down the incident magnetic field intensity, which is going to be equal to EI0 over eta 1. It is pointing out of the board, so we multiply this one with AY. Okay, this is just the AY. And then we write down the projection term, which the spatial projection term, e to the power minus j beta 1 times whatever is in here, okay? Let's change a little bit the angle view. And similarly, we have here E reference, this is equal to E reflected wave intensity divided by eta 1 times minus AY times e to the power minus j beta 1 times the space propagator here, which we can write it, which is x sine theta r minus z cosine theta r, and this is what we get. Then essentially, this is here again for the what is the most important parameter. Always when you have a reflection or transmission, is to obtain the reflection coefficient. And the reflection coefficient here, it is, wait a second, so this should be here. Yeah. So E1 is going to be equal to E incident at Z equal to 0 plus E reflected at Z equal to 0. And this is going to be equal to 0, which we actually directly or simply can conclude that these two terms, which define the reflection coefficient for the parallel polarization, which is equal to ER0 divided by EI0, this is going to be equal to -1, okay? In fact, this is what we obtained also in the previous case, where we had the reflection coefficient for the perpendicular polarization. Okay. Then, everything is on the board for us to go and find two important quantities. And these two important quantities will be the following. So let me take this out for a moment. This boundary condition, so let's erase the previous expressions. So we need to find E1, we need to find H1, okay? And E1, it should be equal to the incident wave plus the reflected wave. So we add these two together, okay? And then we add also these two together, the magnetic field intensities. So we obtain these two terms, and from these two terms, we obtain the time average power intensity, which will be similarly equal to 1/2 times the real part of E1 cross H1. Not forgetting the complex conjugate for the term next to the magnetic field intensity. Now, any question? Can I put it? Okay. If you have no question, we can give it another short break.